starting. Are you able to see the whiteboard?
Yes.
Okay. So we are doing the necessary and sufficient condition when the function is we are doing real analytic function, right? Multinomial series we have done. Then what we did is multivariable real analytic function, multivariable with real analytic function, So next functions. Next we did some theorems, lemmas concerning real analytic function. So concerning real analytic function. Okay. Of course, this is real analytic function is not new to you, but the thing is that multivariable real analytic function is completely new to you. Okay. And of course, we end this last class. We end with this very beautiful theorem that is called a necessary and sufficient condition to be a function, a smooth function to be a real analytic function. What it says, if omega be an open subset of Rn and f is a C infinity function, then if, as we know that if f is real analytic function, this is always the converse is true, that f is C infinity. But the other way around is not true, that there are functions which are f C infinity, but they are not real analytic, as you have given me the example. Then f is a real analytic in omega if and only if for every compact set K contained in omega there exists an M positive and R positive such that this holds. Okay, d alpha of fx is less than M mod alpha factorial R to the power mod alpha for all x belongs to K and for all alpha. Okay, so this, because our aim is to study solutions of a PDE, which is of series form, or we seek a solutions which are real analytic, okay. So this is our main aim of this chapter, that we wish to find the solutions to a PDE which are real analytic. So the first question is whether always we can get it or not. Of course, this depends on the analyticity of the something and the given conditions and the force and all those things. Okay, so this is our aim. Now we first prove this is known as the famous Cauchy-Kovalevsky theorem. Both the name belongs to the very great mathematician Cauchy, and Kovalevsky is another mathematician. So these are called Cauchy-Kovalevsky theorem.
Sir, there is a doubt from the last step of necessary and sufficient condition.
Okay, tell me. Yeah.
That we are varying alpha over all alpha subject mod of alpha equal to n plus 1, then why we are taking only one term in the summation?
I cannot hear you. Again, can you tell me? Please, again.
So in the last step of the proof of last theorem, last lecture.
Last step is the, what is the last step?
So we are taking mod alpha equal to n plus 1 in the summation.
Just a minute. Mod alpha equal to k plus 1. Yes.
But we are varying all alpha such that mod alpha equal to n plus 1. That means there are many possibilities of alpha. Then why we are taking only
last term will be of 1 by k factorial 0 to 1 minus t whole to the power k summation mod alpha equal to k plus 1, right? This is the last term.
No, sir. In
that we have alpha less than equal to n. Sorry, k and n I have mistaken. So it will be mod alpha less than equal to k, right? You agree?
Yes.
Next highest order derivative will be mod alpha equal to k plus 1. You agree?
Yes, sir.
So that is why summation mod alpha equal to k plus 1 mod alpha factorial by alpha factorial d alpha the derivative on the function f of at the point x naught plus t x minus x naught, you know, because that is a remainder term. Now tell me, what is the problem?
Sir, problem is that we are taking m summation alpha equal to k plus 1 and r1 by r whole to the power alpha. Then we are varying alpha in such a way that mod of alpha equal to n plus 1.
Yes.
Then why we are taking only just substituting mod alpha equal to n plus 1? Because there are k power n possibilities of alpha such that mod of alpha equal to n plus 1.
No. Here the possibility is mod alpha is k plus 1. You agree? Yes, go ahead. Yeah, summation over mod alpha equal to k plus 1, right?
Yes, sir.
So what is the problem?
Then, sir, if we take x as n tupled vector, then there are n to the power k plus 1 possibilities of alpha such that mod alpha equal to n plus 1.
Yes.
Then why we are just putting mod alpha equal to n plus 1 and take out the summation?
I haven't taken the summation out. Where I have taken the summation out? Okay, we will discuss it at the end of the class. Okay. Okay. What's your just a minute? Oh, I don't know who are you. So just we can discuss. What's your name?
Devranjan Pandey.
Devendra Pandey. Okay, Devranjan Pandey. We will discuss at the end of the class. Do you have any problem then? Okay, we will after we finish this class, we will discuss it. Okay. It's where I'm not able to understand what exactly you want to clarify. Okay. Clear, Devranjan? We will do that. Okay, we will do. Definitely, we will discuss that. Okay. Anyway, so there's some anyway. So today we will be doing a famous Cauchy-Kowalski theorem. Okay, it's a very famous theorem. First, we will do the Cauchy-Kowalski theorem for ODE. Okay, which for us then for our life is easy in case of the ODE, ordinary differential equation. Okay. First, we will do ODE, then we will do PDE. So what the theorem says, very classical and very old theorem. The theorem says that let f be a real valued function. Okay. Now there is no multi-index come into play. Okay. We are a function analytic at the origin. Then the ODE u prime t is equal to f of ut and u0 equal to 0. It's a simple ODE. Has a solution analytic in an open interval containing 0. Okay. So let f be a real valued function analytic at the origin. This is very important. This f is a real valued analytic at the origin. Then this ODE u prime t equal to f, simple ODE, f ut at u0 equal to 0 has an analytic solution, has a solution which is analytic in an open interval containing 0. Okay. So you will find in these intervals. So R, there is an R. This is minus R. This is R, where the solution is real analytic. Okay. So this is a you can say this is a existence of a you find an R, so that small locally you can always find a real analytic solutions for an ODE provided this function is given to be an analytic. This is very important. If this function is given to be analytic, then you can always find locally the real analytic solutions. Is that the statement clear? The proof is very beautiful. Is the statement clear? Very nice analysis will come into play in proving this theorem. So is the statement clear to all?
Yes, sir.
Yeah. So very simple argument. Okay. Okay. First, suppose that u is a the solution is a C infinity solution. Okay. So we want to show that it is a real analytic solution of the above PDE. Suppose u is a C infinity solution of the above PDE. So you can ask me why can anyone tell me why this is a C, why we can suppose that assume that u is a C infinity solution? Can anyone tell me why? Yes. Can anyone tell me why? Why I can assume u is a C infinity solution? Why? Why this ODE will have a, first of all, why this ODE will have a solution, and then why I can assume that is a C infinity solution? Who will tell me?
Sir, the given equation is u prime equals to FUT. So since because F is analytic, so we can apply Picard's theorem to show that u has a solution.
Has a unique solution, in fact, you can show.
Unique solution, and because u prime is equal to FUT, so differentiating again, you have u double prime is equal to u.
Very good, excellent, excellent.
You just keep on doing that.
So this is not actually an assumption. Okay. Suppose we can always assume that u is a C infinity. There always exists a C infinity solution to the above ODE. But the non-trivial step is to prove that this C infinity solution is in fact a real analytic near origin. Okay. Very good. ODE. So we know that u0 is 0. And what is u prime at 0? F0. Just using the, because u is a solution, we can put it in the ODE equation and we can study this. Okay, u0 is 0, u prime 0 is f0. So so it is given that u double prime t, what will be u double prime t? Can anyone tell me? If u is a solution, huh? What is that? What is u double prime t? Huh?
U F prime ut.
Okay, then
into u prime t.
Very good. And so I can write what is u prime t. Again, I can use this equation. So this is f prime of ut into f of ut. Yes, just I use the equation that u prime t satisfies the equation u prime t equal to f of ut and u0 equal to 0. That's it. Okay. So u prime at 0 is f prime at 0 and f at 0. Just from the above. So in particular, I can do the triple derivative. U triple prime t is f double prime of ut, u prime t, f of ut. Just derive this equation. Okay? Plus f prime of ut, f prime of ut again, u prime t. If you derive this part. Okay. So these imply u triple prime t is equal to f double prime ut. Again, you use u prime t equal to f of ut. So f of ut whole square. Okay. Plus this, again this comes into f prime of u prime t. So this imply u triple prime 0 is equal to f double prime 0 f0 whole square plus f prime 0 square. We want to see how the solutions, all that, because you remember we have to make some series expansion, right, at the point 0, around the point 0. So we were checking that how u prime at 0, u double prime at 0, u triple prime at 0, u n prime and 0 will behave. So what in general I can say that you just look at the triple derivative. So f double prime 0, f0 whole square plus. So these are the, what I can call these are the a polynomial in f0, f prime 0 and f double prime 0. Agreed or not? So triple prime at 0 is a polynomial in f0, f prime 0 and f double prime 0. Agreed or not? Huh? Yes or no?
Yes, sir.
Three odd this polynomial, right? So it's a polynomial because f prime 0 is one, f prime 0 is a polynomial in different thing, in three part. So in general, I can write nth derivative at the point 0 is a polynomial of f0, f prime at 0, dot 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 f. One derivative will be less, right? Because you can see. You just see. You triple prime, so highest order in f prime is f double prime. Okay? So in the same way, we can see that nth prime at 0 is a polynomial. So what we can say is that where Pn is a polynomial in n variable, f dot dot up to n variable. These are the variables. Okay? In n variable with coefficients in Z class. Is that clear? Because you can see Z plus why I am taking, because this coefficient is something 1, this is 1, it might have come 2, 3 like that. It might have. Okay. So u at nth derivative at the point 0 is a polynomial, is an n variable polynomial with f0 with the nth polynomial in f0, f prime, f dot dot, f n minus 1 and 0 with coefficient in Z class. It's simple. Okay. Now you consider this series. Consider series summation n equal to 1 to infinity. Just consider this. We don't know whether this series converges or not, anything. Just consider this series. F0. This is the polynomial f0, f prime at 0, dot dot dot, f n minus 1 is n factorial t to the power n. I consider this. We don't know whether this series converges or not or anything. So I claim is that this Pn is this Pn, okay, where that un prime 0 and u comes. Okay, so the claim is that the above series, the previous page series, the above series means above series has a positive radius of convergence. What does it mean? Can anyone tell me what does it mean? So this series has a positive radius of convergence. What does it mean? Just tell me, what does it mean? What does it mean?
There is some open interval in the series converges.
Exactly. Very good. Okay. Now this is our claim. Now I want to prove this claim. Okay. It's a very nice theorem, very nice, elegant argument. Just see. Suppose, so this is our M now. Suppose G is a real analytic function at 0. And there exists V real analytic at 0 satisfying V prime t is G of Vt and if nth derivative at the point 0 is less than G nth derivative at the point 0 for all. Suppose this, I am supposing, we have to prove this step also. We will see. Suppose G is a real analytic function at 0 and there exists a V real analytic at 0 satisfying V prime t equal to this ODE. So what I am saying that suppose G is a real analytic function satisfying and there exists a V such that V prime t is equal to GVT, V0 is 0 and Fn at the point 0, nth derivative at the point 0 is less than equal to G nth derivative at the point 0. This should hold for all n. Okay. Suppose you have.
Sir, where is F coming from?
F is the same F here. This F. Okay.
Okay, sir.
Just that's the same F. F means which solve this OD in the initial F. Okay. Suppose we have this. Okay. Then we will see that the above series will have a radius of positive radius of convergence. Okay. How to prove this? Since V is real analytic, just now I am proving. Suppose we have this, then I will show that the series we have taken that is that will have a positive radius of convergence. See how? Since V is real analytic, that is the series at 0. So we have assumed that V is real analytic at 0. That means the series V is real analytic at 0 means the series V nth derivative at the point 0 by n factorial t to the power n has a positive radius of convergence, right? Has a positive radius of. I assume that step that V is a real analytic as 0 has a positive radius of convergence. Okay, say R. Let's say R positive. Now let 0 less than R1 less than R. We claim that summation this series F0 converges in mod t less than R. That clear? So we have supposed that there exists a G real analytic function and there exists a V real analytic at 0 satisfying V prime t equal to GVT, V0 is 0 and Fn is this. This is I have assumed this part. Okay. Then I say that if I assume this part, then we can prove that this series has a positive radius of convergence. Okay. How? So that is if V is real analytic, then the series V and t to the power n has a positive radius of convergence. Let's say R. So I just take a point number R1 which is strictly less than R and we claim that this series has converges in mod t less than R1. So how? Any idea how? It's very simple. Pn F0 dot Fn minus 1 0 by n factorial. This is less than what I can say the mod will go inside polynomial. This is a simple thing. F0 dot f of n minus 1 0. Right? By n factorial. Next step, what I can write? Each fn derivative 0 is less than gn of 0. So this is a polynomial. So which is less than equal to Pn of G0, G prime 0, dot up to G n minus 1 at the point 0 by n factorial. Which is equal to, who will tell me? Which is equal to? Which is equal to? What? You use the equation now.
Wait.
We satisfy this equation. Now you do the same trick. V double prime 0 at 0 is G of 0. You do the same trick. So what you will get? Equal to?
The nth derivative of V.
Exactly at the point 0. Just this step is using V satisfies ODE. Okay, excellent. So what you can say now? Is that converges now? What? What happened? What happened? So this immediately imply summation Pn f0 f prime at 0 dot fn minus 1 at 0 by n factorial t to the power n is less than this summation, this modulus Pn dot t to the power n, which is less than summation Vn at 0 by n factorial t to the power n, which is finite if we choose mod t less than r1. Agreed? So these imply summation Pn f0 f prime 0 dot up to fn minus 1 at the point 0 by n factorial t to the power n has a positive radius of convergence. Positive radius of convergence. Agreed? Clear? What happened? Is this statement clear?
Yes, sir.
Okay. Now can you tell, but I have assumed a big statement right here, that there exists such G, there exists such V, such that V prime T equal to GBT, such that these Fn derivatives, so many things I have assumed. With that assumption, I have proved that this series has a positive radius of convergence. Now suppose we have still that assumption is valid. So now I can define. Can you tell me what should be the solution, real analytic solution now? Ut should be equal to summation n equal to 1 to infinity. This makes sense. Pn f0 f prime 0 dot up to fn minus 1 at the point 0 by n factorial t to the power n with mod t less than r1. Then clearly u is real analytic. Of course, which we have proved it. U is real analytic. Real analytic. Okay. And what is u0? U0 is clearly u0 is 0, and you can check also. You can check immediately that u prime of t is equal to f of ut. Clear? Because just this is that clear? What happened? What happened?
Sir, how is u prime equals to f
You
of?
tell me. That is why I asked you why. Why? Huh? Why? So this I give you exercise. Otherwise, I will prove it next class. Check. Very simple. You check. Okay. Exercise. Please check this. You can see in the book or somewhere. Please don't see. You check this. Why this u prime t equal to f of t. Okay. Is that clear? Is that clear? Here you have to use that f is also real analytic. Okay. Clear?
Yes, sir. Yes, sir.
So you have to check f is given real analytic. Let's see. Just use that, nothing else. Okay. So you have proved this theorem. Agreed? But with a pinch of salt. What is that? We have to prove this. Then you agree that this is a real analytic solution? All of you agreed? All of you agreed? Sanjeev, Devranjan, Deepak, Kritika, Manish,
Yes, sir.
Ekans, Shammi, Nirmal.
Yes.
Everyone agreed? So this is a Yash. Vivekanand agreed? Okay. So, but now we have to prove this statement. If we can show this such G exists, such G and V exist with this properties, then we can say that yes, we have this thing, everything is there. So we have this series, and we prove this series has a positive radius of convergence, and we define UT is like that, and we say that U is real analytic and U0 is zero, and it is very clearly we can prove that U prime t equal to f of ut just using the fact that U is given to be real analytic at the point. Sorry, f is given to be real analytic at the point. So this is a solution. This is your desired solution. But here to prove this desired solution, we have assume a very big step, which is that we have to find such G and V such that this satisfies. Okay. So next step, the last step, we will show that existence of G and V. Okay. So existence of G and V. Okay. Since F is real analytic at 0, this implies there exists R1 positive such that summation n. This is a definition of real analyticity. If nth derivative at the point 0 by n factorial R1 to the power n converges. Agreed or not? Agreed or not? Yes or no? F is given to be real analytic at the point 0. That means there is a positive radius of convergence, and I take some point from that positive radius of convergence R1, and I say that this series converges. Yes or no? Agreed?
Sir, this R1
Yes.
Yes.
Sir, this R1 is not same as the previous one, right?
No. There is nothing to do with this R1.
Okay. Yeah.
R bar you take. Just for our. This is nothing to do with that R1. That is any arbitrary R1 I have chosen from 0 to R. Okay. This implies this series convergence. This implies there exists a C positive such that the nth term of this series R1 to the power n is less than equal to C. Agreed? So this implies if nth derivative at the point 0 is less than C n factorial R1 to the power minus n. Just take R1 here, n factorial here, nothing. Okay. So this. Now define GT is like that. C1 R1 to the power minus n t to the power n. I just define. Of course, we have to show that this series has a positive radius of convergence. So these I can write at n0 to infinity C1 t by R1 to the power n. This I can write like this. Now, then G is real analytic in mod t. This is when this is less than 1. That means when mod t is less than 1. Clear? So this function is well defined and it's a real analytic function when mod t is less than R1. Okay? This R1 is that the same R1 I have getting from here. There exists an R1, I take that R1. Is that clear? Is that clear? If you don't like R1, you take R. Okay? Clear?
Yes, sir.
How I define the function G. Now tell me, then what will be G nth derivative at the point 0 for this function? What is that? This is a real analytic function, so the derivative will go inside. You take the derivative of t to the power n t to the power n minus 1, the g prime t, and then g prime t at 0 is 0, like that. So what will be g nth derivative at the point 0? Huh?
So C times n factorial by R1 is power n.
Exactly. This will be C times n factorial R1 to the power minus n. and you just look at it. How I define f, what is this? So this is c times n factorial r1 to the power minus n, which is greater than f nth derivative at the point 0. So this is nothing but this is greater than modulus of nth derivative at the point 0. This is the way we have defined, right? Fn is, so there exists a c, you take that c only, not c, that c only. Okay, c that for which is less than c. Okay, so we have, so first statement is done. I have defined some function g whose this is done. So I have defined a function g such that the nth derivative of g at the point 0 is greater than modulus of f, the nth derivative at the point 0. Clear? So it is done. Now what I have to find? I have to find the function v, because g has to satisfy. If you remember, we have to define some v prime t is equal to g of vt. G is real analytic. The way I have defined this is real analytic. Then I have to find v, which is real analytic as well, and v0 is 0. I have to find now v. Now what to do? And anyone know? Now we want to find a real analytic v satisfying g of vt v0 equal to. That means we know what is g. V prime t, we already have the value of g. G is this. So this is what is g? Summation n equal to 0 to infinity c times, what is that? What is that? What is gvt? Right? Yes or no? Because I define gt is like that. So g of vt will be summation c vt by r1 to the power n. Clear? Now if I do the sum, of course mod of vt is less than r1. So this is, if I do that, this is c, the integral will come, summation will come as r1, so 1 by 1 minus vt by r1, which is equal to c r1 by r1 minus v. I have to solve this with 0. Exactly right? Am I right? Am I right?
Yes, sir.
This step to this step, it is clear? Huh? Geometric series. X to the power n, 1 by 1 minus x, if mod x is less than. Of course, I have assumed vt is less than r1. Is that clear? Is that clear? You can always make this vt less than r1.
Yes, sir.
Okay. Now we have to solve this ODE. How to solve this? This is nothing but you just multiply r1 v with v prime t. Okay. So you will getting we will be getting v prime t r1. Okay. Minus v prime t v minus c r1 equal to 0. Okay. So this I can write as this is half v square prime minus r1 v prime plus or minus what will be because I have taken minus plus cr1 equal to 0. Now integrate both sides. So v prime c. So this I will get half v square t minus r1 Vt plus CR1 is equal to 0. Why I should get some C constant. Why that constant is 0?
V0 is equal to
Exactly. Or V0 is equal to 0. Okay. No. Then I will get some other constant, right? No, right. V0 is equal to 0. I have used here this fact. Now this is a quadratic equation in V. So if you solve this, you will get Vt is equal to R1 plus minus root over R1 square minus 2C1 R1T. You just use the B square minus 4AC by 2A. That because this is a quadratic. So what I will take, plus or minus? Who will tell me? Out of that, what I have to take, plus or minus?
minus
Why?
V is less than R1.
Exactly. Excellent. Because this is equal to this whenever if and only Vt this series is convergent less than R1. Okay. So if I take plus R1, then R1 plus some positive quantity, which is not possible. So I have to take Vt. The required Vt is R1 minus root over R1 square minus 2C1 R1T. And you can clearly check that V0 is 0 and of course Vt is equal to R1 root over 1 minus 2Ct R1. Okay, and clearly you can check why V is real analytic. Can anyone tell me? Huh? What happened? Why it is real analytic? Check this. This is nothing to check. Why V is real analytic?
Sir, if we take the t sufficient in a defined neighborhood around 0, so we can make square root this function to be analytic. And
this is 1 minus x to the power half. When x is less than 1, you can have a series expansion, right? This is 1 plus I think half x square plus something dot dot dot. Okay, so this you do this R1 1 gets cancelled and you will get a series in t by R1. You will get a real analytic t by R1. When t is less than R1, this series converges. Okay, so clearly V is real analytic, V0 is 0 and it satisfies V prime t is equal to G of t. See how beautiful the proof is. Okay. So this completes the proof. This completes the proof. Okay. Any question? Just I can wait for. I will wait for 1-2 minutes and then please have a look on your page. Do you have any question? Then. Is that clear? So we proved the Cauchy covariance. So the next question is remark. Why there is a unique real analytic solution can. So I found. So what is the statement? Statement is what is the statement? Where is the statement? What is the statement? Oh. So I can uniqueness I can add. Why? Why? So I can say that if the real valued function analytic at the origin, then the OD U prime t this has a unique real analytic solution in an open interval containing the locally. Why there is a locally unique real analytic solution? Why? Why? So I prove analytic and open interval 0. Why it's unique?
by Picard's theorem.
Exactly. Because by Picard's theorem we'll always get a unique C infinity solution locally. Uniqueness is locally. So by Picard's theorem you always get a unique real C infinity solution, and I prove that C infinity the unique C infinity solution. Now I prove that there is a real analytic solution locally. That means that solution is equal to the C infinity. Is that clear? Because theorem will always give you this. When I ask you, suppose U is a C infinity solution of the O. So suppose U is a unique C infinity solution. Uniqueness is always local property. Okay, there is a unique C infinity solution of the above. Now we prove that unique solution is in fact a real analytic. So now we can restate the theorem as we have a unique real analytic solution around 0. Clear? That is the Cauchy-Kovalevsky theorem. Okay, this is provided this capital F is given to be real analytic. Okay, because there, of course, if capital is local ellipsis, so you can apply the Picard's theorem. So you will get a C infinity. You can get a solution, C1 solution. Now using the bootstrap argument and the U prime T F, if U is a solution, then U prime is also defined. Then you take the derivative, and F is C infinity, so U is also C infinity. Now we prove. Now this theorem I prove that now this U is a C infinity solution is in fact a real analytic solutions. Okay, hence this proves the Cauchy-Kovalevsky theorem for ODE. Okay, very good. Now our aim is to prove such theorem for PDE. Can anyone tell me to prove this type of theorem in PDE, what setting I have to use? Somehow I have to bring that PDE into some ODE. Which type of ODE? System of ODE, right? We have seen this, right? Like when we are doing characteristic equation, what we did, we write a system of ODE, right? And we solve that, right? So same thing. So for that system of ODE will be, there will be U1, U2, dot, 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 UN, and very complicated, right? The coefficients matrix and all those things. This F of UT is very complicated. It's like a matrix. It will be a matrix. That time, so for that we need to understand the real analytic for a multivariable functions. Okay, that is the reason we are interested. Last 2 class we are doing the real analytic function for a multinomial for x to the power alpha, where x is a vector and alpha is a multi-index. That is the reason we are doing that. So now our aim is to prove that Cauchy-Kovalevsky theorem for PDE. Before that, before proving that Cauchy-Kovalevsky theorem PDE, we will prove that something for system of ODE. That's not just U prime T of UT. U prime is now a vector. F is now not just a scalar. It's now again a matrix kind of thing. We will see. Okay. Before that, this is our aim. Before that, let us prove some theorem. Okay. Define some notation. Define some new definitions. Okay. So one Cauchy-Kovalevsky ODE is done. Now our aim is to prove Cauchy-Kovalevsky for PDE. Okay. Then the life is of course difficult. Let us fix some definition. Let omega Rn be an open set. 0 belongs to omega. F comma capital F is a map from omega to Rn. So it is like f of some x is nothing but this is f1 of x dot dot f m of x. Kind of similarly f of x, where x is something from omega. This is f1 of x dot 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 f m of x. Then it's okay. So this is the mapping from Rn. Okay, it's a vector valued function. Okay. Then we say that f is majorized by capital F if d alpha, this alpha is a multi-index, fk, k means one component, some component k, fk at the point 0. The same thing we want to do it for vector valued function. Same we have done there now. That you remember f of n at 0 is less than gn at 0. You remember? Same thing we call f is majorized by capital F. Okay, we said here the small f is majorized by g. here we say that small f is majorized by capital F if d alpha is the, this is the partial derivatives with alpha is the multi-index, k means the one component of small f is less than this. This should hold for every k and for all alpha in the multi-index. For every k means f1, f2, f3, fn. For every f1, fk, d alpha of fk, then we call f is majorized by capital F. And in notation we write, capital F. Okay. Now a small theorem. You can understand same proof I have to do for the system of ODE, but there this G we have to find that G, but that time this G is a vector valued G. Okay. So let the very beautiful theorem omega to R be real analytic as 0 belongs to omega, then there is still C positive and R positive such that what does it mean? Given any real analytic function which is real analytic at 0, given any function f from omega to R which is real analytic at 0, okay, which is real analytic at 0, then there exists a constant C and R positive such that f small f is majorized by this function. This is, let's say, some capital F or some capital F. Okay, just a minute. Hello. मैं अभी कुछ बात नहीं कर, मैं अभी बिजी हूँ, बाद में फोन. Small f is majorized by CR by this function. Okay. What does that means? What I have to prove? What I have to prove? Who will tell me? What I have to prove? What I have to prove? Huh? That means I have to prove this. D alpha of fk at 0 is less than this. Clear? So let me prove this. Since f is at 0, there exists R positive such that alpha d alpha f at 0 by alpha factorial. Same thing. This implies there exists C positive such that d alpha f0 by alpha factorial r to the power mod alpha is less than C, and this is d alpha f0 is less than C r to the power mod alpha. Okay? Is that okay? Same trick. Now right hand side function CR by R minus x1 plus x2 xn. C times 1 minus x1 by R plus x2 by R plus xn by R. This function, what I can write? Who will tell me? This we have done. What happened? Huh? What happened? You don't remember this?
Sir,
Sum of drifting.
Yeah, Tell me.
Like x1 by r1 plus x2 by r2 plus x1 by r1 raised to power n, where n1 raised to infinity.
Alpha mod alpha factorial. You remember? You just check in the first class of this chapter I have done. X1 by r. The proof also I have used the multinomial theorem. N by r. Clear? Agreed? All of you agreed? So this is summation alpha c mod alpha factorial by alpha factorial r to the power minus mod alpha. Clear? Clear or not? So this is CR. So this is a, you know that this is a real analytic when mod x, you know what is that, when mod x is less than this. Clear? When mod x is less than r. So what will be the derivative of now? CR by r minus x1 dot xn. This will be this real analytic, so that we know the real analytic function. Then the d alpha is also real analytic function. That means the derivative will go inside. We all know all this theorem we have done. So this will be C. What will be the d alpha? Tell me. If I take the d, here is alpha alpha. If I take the d alpha, so what will be the this in the right hand side? Huh? What will be the right hand side? So this will be d alpha times this. You remember alpha greater than equal to beta. You remember? Now here alpha and beta is same. So what will happen? This we have done Leibniz rule. We have done in the first class. You remember? You check. You will get C mod alpha factor. This will be 1. That's it. So we get d alpha CR by R minus x1 plus x2 plus dot xn. This is equal to C times mod alpha factorial r to the power mod alpha. And what is this? What is this?
Greater than equal to.
Exactly, it is greater than equal to d alpha if c. Okay, so this implies d alpha if at 0 is less than d alpha CR by there exists a C and R such that this happens. This implies small f is majorized by C because there is no component one f is just not a vector vector by R minus 1 plus 2. Clear? Is that clear? Clear? Now I will do a Cauchy-Kovalevsky theorem for, so any f which is real analytic at the point 0, at the point this is always majorized by this function. This is not a trivial proof, not a trivial idea, right? It's always, the proof is very simple, but there are many very nice steps. So you have to be careful. Whenever the f is given to be real analytic at the origin, then you can always majorized by such functions. Okay. Same thing, right? Good. Okay. Now we will prove this beautiful and quite a complicated theorem. Of course, the proof is not that complicated. Let Aijk and Bj be defined on Rn minus 1 plus. So it has this type of variable, right? N minus 1 plus m variable, okay? And is analytic at the origin. Then the system of PDE this is the system. This system of PD, ODE, del u by del xn equal to summation ai jk and this with the initial condition. Condition uj equal to 0 on xn equal to 0 or j equal to, it's trivial, right? So del u by del xn. So I take the initial condition xn equal to 0, that is Rn minus 1 plane. Rn minus 1 plane, uj's all are uj all are 0. Okay. This is a system of ODE. Okay. I say that this system has a, and given aij and bj are real analytic, which it has a unique real analytic solution in a neighborhood of the same thing, same statement, but now it's a life is complicated. We are doing a for a system of ODE. There is one ODE. U prime t is f of ut. Instead of here, now we have del u by del uj. So uj is j equal to 1 to m. So there are m ODE, right? System of ODE. So your capital U vector is nothing but u1, u2 dot un. So del u by del xn. This is okay. So right, left hand side is del u by del xn. You can write down as a system of ODE. Sorry, here I missed del u by del xn. Okay. Okay. So this system of ODE will also have a. This is I can understand. You can think of what is this system and all those things. This is very simple. So this is a very simple system of ODE. You can take if you don't like n, you take 1, 2, 3, 4, 5, 6 like that. Okay. This is a system of ODE. I say that if this coefficient matrix, this coefficient vector are real analytic at origin, then you can have the solution. First of all, why this has a smooth solution? Of course, again you can use the Picard's theorem. So just tell me, all of you know the Picard's theorem for system also? Huh? All of you know the same, right? Picard's theorem for system. All of you know system of ODE? Yes? Do you know or not? Don't know? What is?
Yes, sir, we do know. You know.
Okay. Okay, good. So automatically you will get a C infinity solution. Again, since they are all these all are so all these coefficient matrix are real analytic. So you will always get a system. So okay. So now I will prove this. Step 1. Of course, if you don't want to understand the proof, just listen and then forget it. At least you should understand the proof for that ODE, that simple Cauchy-Kovalevsky theorem for ODE. The same proof I will do with more this type of multi-index, because of this system, the life is quite difficult. Nothing more than that. Okay, the proof. If you don't like the proof, you don't have to study this proof. At least just listen properly for this class only. That's all. Okay. Since aijk and bj's, the coefficients, this coefficient matrix and this coefficient and this matrix are real analytic. Are real analytic 0. So this implies just now use this theorem. You can use this theorem, right? Use this theorem. Okay. This implies there exists a C and R positive such that AI JK is majorized by CR. AI JK is a function of n minus 1 plus m variable, right? So CR times R minus x1 plus dot 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 xn minus 1 plus u1 plus dot 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 u1. Okay, and Bj is majorized by CR, same thing, R minus x1 plus dot 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 xn minus 1 plus u1 plus dot dot dot. Okay, this is just applying the previous theorem. Applying okay, clear? Is that clear? All of you?
But there, sir, it can be possible that two different C1, C2, and R1 are
That's why I'm asking. Yes, very good. Why there is a same C1? You take the, so you will get R1 and R2. If you take the minimum of R1 and R2, then this series is done. Right hand series also convergent, this series also converges. Clear? Is that clear now?
Yes, sir.
So you remember the series has to, if you see the proof, for that proof, if you see the series to be convergent, we need that this x1 is less than R. So this R1 you will get for the same, R2 you will get. So you take R equal to minimum R1, then both the series will work, right? Yes or no?
Yes, sir.
Good. Now step 2. Prove this. Step 2. Consider a system of, consider a PDE, ODE. Del Vj by del Xn. CR times R minus Xi, I equal to 1 to n minus 1, and minus summation Vi, I equal to 1 to m. This PDE, ODE, sorry. 1 A equal to 1, I equal to 1 to n minus 1 comma m del Vk by del Xi. Consider this ODE system. Again, J and with the initial condition. Again, you can ask me why this system has a solution or not. Okay, I claim that consider this PD with the initial condition. Just same thing, G. You remember G and V. We have to be complicated. Here the things is little bit complicated. Same thing with the initial condition. Vj is equal to 0 on X. So this is again a different ODE we consider. Okay. Now you have to show that this ODE has a I claim that this has a real analytic solution in a neighborhood of origin. Same thing that G and V. We define a function G, real analytic function G, and V prime t equal to G of Vt, so that V is also real analytic. You remember? Same step. So here little bit complicated. Now you tell me why this has a. I will prove this step. Proof of step 2. Let, this is a very nice trick. Vj is you make a two variable function. X1 plus X2 plus dot 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 xn minus 1 comma xn. For all j, I define this function. Vj of x1, x2 dot 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 up to xn, I define it like that is equal to w of x1, x2 dot 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 xn minus 1 comma xn. Okay. So this I name it S variable and this I name it T variable. Then This is a very easy check. Check Vj solves this equation. Vj solves this equation provided W solves del W by del T at the point St R minus S minus M W of St 1 plus M into N minus 1 del W by del S, and W is, I say that let Vj define this, and then Vj solves this equation, provided W solve this. This is very simple. Okay, is that clear? Tell me, is that clear? Huh? You just check, man. Just check here. You will get it. Okay. If then Vj solves provided W solves this. Okay. You just check del V by del Xn. You just use del W by del Xn by del S by del Xn, and then W solves this equation. Then you will see that this Vj solves. This is a very nice trick, and of course this doesn't come very easily. Okay. Okay. Clear? Okay. Now you have to solve this. That means Vj solves this. Now if you solve this, then you get the solution Vj for this. Now you tell me how to solve W. Can anyone tell me immediately? Can anyone tell me how to solve this W immediately? Huh? Just think, we have been doing this last 10 lectures. How to solve? Like U of xy, ux, uy, uuy, all those things. How? Method of? Now this is a function of W is a function of two variables. What is that? Wt st minus cr by r minus s minus m w of st 1 plus m into n minus 1 w s of st equal to 0, and ws at 0 is 0. So if you don't like s and t, you make x and y. X is 1, r, y is in r. How to solve this? Huh? Method of
characteristics.
Yes, it's a two variable function, s and t. You just use x prime t, that dx by dt will be 1, dy by dt will be this term, and dz by dt will be this term. If you solve this, one can just one line, one can solve using method of characteristics. And life is easy because this is 0. That you remember u of x comma 0 is gx. Now g is 0. So it's very easy. Method of characteristic and obtain ws of t is equal. You can check that nothing is difficult. It's not at all difficult. Okay, you can see this is the solution. Dz by dt will be this cr by r minus m into n s of t dz by dt. Okay, if you check and you will get this. Okay, so you have a solution to this v, which is v0 is 0. You can dub because from here you will get v0 is 0 and all those things are getting. Okay, okay. So step 2 is proved. Now the final step. Step 3. If uj is a solution to our original system, or this is solution to of the original system of ODE, then uj is 0, d alpha uj at 0 is 0 for alpha equal to, of course, because that is derivative, because you know uj is 0 in the initial condition when xn equal to 0. So you cannot take alpha to be alpha in, right? Because that variable has to be 0. Okay, and you can check del uj at the point 0 by del xi is equal to dj at 0. In general, I can write d alpha uj at 0 is pj alpha bj at 0 d beta. It's complicated. D0 dot dot dot. I am not writing that. So you can write in general. Same thing. U prime t, u prime t at 0, u double prime t, u triple prime t is a series, is a polynomial of f0 f0. So here is the polynomial bj, d beta of bj, then d gamma of a, I, j, k, and all those things will be there. Okay, same thing. You can check that. There's nothing to check. So where? So now define. We just define this function. Ujx summation alpha alpha dot 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 x to the power alpha. This all are multi-integers now. This makes sense. You know why? The solution of the PDE, sorry, system of ODE. You can again check side by side. All are majorized by this type of function. Majorized by this type of function. Once it is majorized by this type of function, you know that we have to find the solution for that PDE ODE which has a solution. A system of, this is a solution of the system of ODE. And this completes the proof. This completes. So if you don't like this proof, of course I understand this is too much multi-index and all these things are coming. So at least you should understand the Cauchy-Kovalevskaya theorem for single ODE, not the system. Okay. Now what I will do, no, I will stop here now. But what I will do that in the next class, I will, once this system of ODE is there, when I will write down the PDE in a system of ODE, and now then I evoke this theorem that we already proved the Cauchy-Kovalevskaya theorem for system of ODE, that it has a unique real analytic solution near origin, and this will prove that the PDE has a system, PDE has a real analytic solution. Just one more step is there. Just how to, only one more step is there to, now not more than a new theorem is that the PDE will always have a unique real analytic solution locally. That proof requires what I have to do. I have to make that PDE into an ODE. Once I make this an ODE, we can evoke this system of ODE theorem to prove the statement. Okay, that's all. You understand? All of you understand what I wanted to tell you? All of you understand? So today we have done two things. One, I have done the Cauchy-Kovalevskaya theorem for single ODE. Then we have done Cauchy-Kovalevskaya theorem for system of ODE. For the system of ODE, now I will do a next theorem, that Cauchy-Kovalevskaya theorem for PDE. For the proving a PDE, what I will do, there is some transformation. I make the transformation to I will make the PDE into a system of ODE and then evoke this theorem. That's all. That's all. Then this will prove the Cauchy-Kovalevskaya theorem for system of PDE. Is that clear? All of you clear?
Yes, sir.
Clear? This is the next step. So the syllabus is up to this much. Okay, the syllabus is up to Cauchy-Kovalevskaya theorem for single ODE, not the system. Okay, but of course, the multinomial real analytic functions are there in the syllabus. Okay, so today is the lecture number 11, right? Or 10 or 12? What is that? 11, I think. I think 11. So that much. Okay. Is that clear, all of you? So syllabus is today up to today's only first part. That real analytic. You understand what I function. Is that okay? All of you? Do well. Best of luck for your minor. Okay?
Yes, sir.
Okay. All Sanjeev. Devranjan, you want to ask something? Others can leave. Devranjan can stay. Yes, Devranjan.
Yes, sir. Can you open the last sheet of last lecture?
Just a minute. Just a minute, Shraddha. Just wait. Others can, you can switch on your video if you wish, so that I can understand better. Yes, yes. Thank you. Just a minute. I'm not getting my notes. Yes, got it. Tell me. Which step? Yes, Dev. I cannot hear you.